Some of the hardest problems in the world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
Welcome to the Space Policy Show. We are so excited you could join us today. We have a great episode. We are talking with Jim Vedda and George Pollock about Cislunar Stewardship, planning for sustainability and cooperation. As usual, please engage with us on Twitter using the hashtag #TheSpacePolicyShow or comment in the video box below on Vimeo. You can also sign up for our latest news updates at aerospace.org, and that's where you can find the paper of the same name, Cislunar Stewardship, Planning for Sustainability and Cooperation. Just a quick intro for Jim and for George. Dr. Jim Vedda is a senior policy analyst in the Center for Space Policy and Strategy at the Aerospace Corporation. Since joining in 2004, he's been responsible for performing policy research and analyses for various U.S. government customers, including NASA, the FAA, the Department of Commerce, the Air Force, the NGA, among others. He's also the author of numerous articles and conference papers, as well as 2 books. My 2 co-hosts have joined me here. I'm sure you can see them. This is Corbin Dallas. Dr. George Pollock, the fourth, is the Associate Director of the Astrodynamics Department at the Aerospace Corporation. He leads a team of analysts providing space domain awareness and advanced space mission analyses for the U.S. Space Force, intelligence community, and NASA customers. Let's kick it over to you, Jim, to get us started.
Okay, thanks, Rebecca. And welcome to everybody who's tuned in. Glad to have you here to talk about the movement out into cislunar space. You know, it's been more than a half a century since we have started seriously looking at how humanity can move out into the solar system. And for much of that time, it has been something that has been fantasy and science fiction, and very slowly becoming reality. Well, we're at a stage where we are going to be looking at expanding the number of applications that we do in space and the amount of area that we cover in space as we do them. We'll talk about some of those in a few minutes. So you should think of cislunar space as the local neighborhood around Earth. Imagine when you were a child growing up and you had restrictions to playing in your backyard. Well, your backyard in this case is analogous to low Earth orbit, or LEO, and geosynchronous orbit, or GEO. That's the close-in backyard area where we've been doing our space activities. But now we're going to expand beyond that, and growing a little bit, our child is now going to move out into the broader neighborhood. And that's a stepping stone to moving beyond. Now, in real life, we don't go from playing in the backyard to intercontinental journeys. We have a period of time when we broaden our horizons along the way. So what we have to recognize is that cislunar space is the stepping stone to everything that follows in human activity in space. It is the training ground. It is where we're going to find out how we are going to manage our operations and achieve more independence from Earth as we move outward. But before we start talking about the specific applications that we're going to be doing there, we have to talk a little bit about the definition of cislunar space, because not everybody really understands what that reference means or how extensive it is. And for a bit of clarity about the definition of cislunar space, I'm going to turn it over to George, who's a guy who can actually do the math on these things. So, George, if you could explain that for us.
Thank you, Jim. It's a pleasure to be here today, and thank you all for joining us. The term cislunar refers to anything that happens between the Earth's surface and the altitude of the moon's orbit. Now, in the community, we'll hear that term applied to cislunar orbits, cislunar space operations, and other various activities and goings on. So it's important for us to understand the scope and scale of this volume. Certainly, cislunar is a tremendously large area. Like Jim said, the orbital neighborhood is far bigger than our local backyard in direct Earth orbit in LEO and GEO that we may be accustomed to. The moon is about 250,000 miles away from the Earth, and it orbits about every 4 weeks. And there's tremendous volume of space that satellites and spacecraft may transit, going from the Earth to the moon. It can take days to weeks. Many of the orbits that we're going to talk about in a little bit, we'll find don't strictly stay within the altitude bubble defined by the moon's orbit. So practically speaking, when we talk about cislunar orbits and cislunar space operations, we kind of fudge it a little bit on the high side of the altitude that we're talking about, because the physics don't really neatly align inside of the bubble defined by the moon's orbit. So we'll get into some of the specific orbits in a little bit, and I'll show you some really cool graphics that Dr. Jonathan Hayes from our team in Astrodynamics department has put together. It's also important for us to talk about the different destinations that we might encounter as these activities expand in the cislunar arena. There are a number of things one might do in direct lunar orbit, like mapping and remote sensing missions. NASA and other nations have undertaken many missions to map the moon, looking for an understanding of its geology and resources that may be there for future use. There are also orbits that don't go directly around the moon, and these tend to be aligned with what are called Earth-Moon Lagrange points. So these Lagrange points are points of relative gravitational equilibrium, where if we imagine for a moment that the moon were in a perfect circular orbit about the Earth, then the particular points, there are 5 of them in the Earth-Moon system, these Lagrange points, if we could place a satellite there and it would stay put. Some of them are unstable, and so if we slightly get it off of that point, then it would tend to wander away. 2 of the 5 are stable, and the satellite placed there would stay there for quite a while. Now, in real life, there are some complications to that, and we'll discuss that perhaps a little bit longer in the next section when I show some of these orbit graphics. But these Lagrange points really enable unique orbital behavior and some really kind of surprising applications that we'll get into here as we go on through the discussion today. So next, let me pass it back to Jim, and we'll talk about some of these new activities, and then I'll kind of explain how these orbits can uniquely enable specific mission applications.
So we have a certain set of applications that have become more or less traditional in space activities, and we're all quite familiar with them and take them for granted, and that would be communications and navigation and remote sensing of various kinds, and that is to include weather monitoring. Well, we're getting to a point where we're going to move up to a new plateau where there are going to be additional applications that are going to be not just experimental things like on the International Space Station, but more routine activities that will include putting more space platforms on orbit in various orbits that will have functions such as doing research in a laboratory setting, doing manufacturing on orbit, and of course habitats for any humans that are facilitating those activities. We are talking about putting research outposts on the moon. To what extent is yet to be determined, and their exact placement, but we're planning to have the moon as a base for research operations that could lead to processes such as the extraction and processing of extraterrestrial resources for use in space and maybe even someday back on Earth. The cislunar space area will be a training ground and probably a staging base for movements to other parts of the solar system, and operations there will need to be able to support that, and that will involve adding things like more habitats and even some storage depots. Now, any terrestrial industry that's in, for example, the trucking or shipping business doesn't just have trucks and ships, they have storage depots as well. most likely the same thing is going to be happening in space. Those who are moving around people and raw materials and manufactured products are going to have some in-space storage, and that's where some of these lunar orbits may come in handy at some point. So all of these activities that I just described, although they are not yet up and running, they are things that would appear possibly in the next decade or so, or at least within the span of a single human lifetime. And given that, we have to consider what type of environment they are going to be working in and how we should sustain that environment so that we don't mess it up in some way that will be a detriment to future activities in that environment. So at this point, I'll pass it back to George so he can give you a look at a little bit more about what those orbits and that environment entail.
Thank you, Jim. So what are these new orbits that we're looking at in cislunar space? And then we'll talk a bit about some of their applications. So as we begin this journey, let's bring up the first video. And here we see a collection of orbits that are depicted in the Earth-Moon rotating frame. Now we've taken the liberty of rotating the camera in this animation around so you can get a sense of three-dimensional perspective. The orbits in the Earth-Moon plane occur around each of the 5 Lagrange points. And maybe let's run the video again so we can elaborate a bit. So there are orbits in the plane. Those are called the Lyapunov orbits. You can see that in magenta, dark magenta, green, and yellow. Shown for scale is the black geosynchronous Earth orbit belt. So you can see we're talking about distances far greater than we tend to operate Earth orbiting satellites today. And some of these orbits allow us to have some out-of-plane motion. Those are the orange and light blue orbits depicted there about L1 and L2. Additionally, there are some very stable orbits that are very similar to the magenta ones in this diagram. And those are called distant retrograde orbits. They actually can orbit the moon and have tremendously great stability properties. So they're so stable that NASA was envisioning using them for the asteroid redirect mission a few years back. And that concept involved robotic mission to retrieve a large boulder from an asteroid, coming back and park it in the distant retrograde orbit encircling the moon, and then later sending astronauts out to visit it and take samples and bring them back for study. So the stability of some of these orbits allows objects to remain in place for centuries. Some of the other orbits are not so stable and need to be actively maintained. The halo orbits are great examples of that. So those are the ones that have that out-of-plane motion depicted here, going below and then above the orbit plane of the moon. Let's zoom in a little bit on halo orbits and play the second video. So you can see here the blue orbits are L1 halo orbits and the orange ones are L2 halo orbits. In this case, these families are what are called southern halo orbits. That is, they have a long loiter time over the southern lunar pole. You can tailor these orbits to linger over the south pole or the north pole of the moon, and you can imagine how that could be really advantageous for communication missions if you need coverage of a given lunar station on the surface. The L2 orbits in particular are very noteworthy in the sense that they allow continuous line of sight for communication satellite to talk between the Earth's surface and the far side of the moon. And in fact, China in 2018 launched a relay satellite that is operating today, now presently in this lunar orbit like these L2 ones depicted here, so that it can enable the relay communications for their far-side lunar lander that they set down on the lunar surface in January of 2019. The green orbits depicted in this video are frozen lunar orbits. These directly orbit the moon and to a lesser extent make use of the three-body Earth-Moon combined gravity the halo orbits leverage that extensively. The green orbits are so close to the moon that it's really dominated by the lunar gravity. And there's a peculiar thing about orbits that are at low altitudes around the moon. The moon is such a lumpy composition that any low lunar orbit that's just randomly put out there tends to have a lifetime measured in days to maybe months at best. The orbit stability is quite poor, frankly, for long-term missions. Those frozen lunar orbits enable long duration missions. You can much more readily keep the orbit where you wish, and those could be well suited to deploy in a constellation for communication or navigation purposes in the future. The orbital environment around the moon is substantially different than what we're accustomed to for operations nearer to the Earth. For example, low Earth orbit satellites are nicely shielded by the Van Allen belts from the intense deep space radiation environment. So we're going to have to deal with much more radiation than we might be accustomed to for some of our satellites. And in many of these orbits, we have essentially perpetual sunlight. There's no eclipsing or very infrequent eclipsing from either the Earth or the Moon. And we have much longer distances as depicted in that first video. We're accustomed to trying to track objects in orbit out to GEO and maybe a bit higher for the things that have been disposed above GEO. But the range out to the lunar distance is about 10 times farther. So space domain awareness becomes much more difficult due to those long ranges. Our telescopes and radars have significant roll-off of their sensitivity at those distances. And in some cases, we also have challenges by virtue of trying to find things that are close to the moon. You can imagine looking for a firefly essentially next to a headlight. That's sort of the challenge as we look maybe from the Earth towards a full moon, trying to find a sunlit satellite that's operating near there. The challenges that I mentioned there, can all be tackled with appropriate application of engineering and operational experience and leveraging experience from Apollo and prior robotic missions. But the message that Jim and I are really aiming to highlight these days is that we ought to leverage lessons learned from our prior space operations in Earth orbit with respect to establishing a sustainability paradigm that can set us up for a long-term good stewardship of this Earth-Moon neighborhood. So I'm going to turn it back over to Jim so we can talk about some of those lessons we've learned over the years since the advent of the space age in the 60s and how we might begin to translate those into this new environment.
George, listening to you and thinking about this as we were writing the paper, it's just staggering how much our perspective has to change to expand into cislunar space. Now, all of our careers, we've been talking a lot about the goings-on in LEO and GEO, and GEO's always been the high orbit. It's way the heck out there. GEO is just far reach from the Earth. But then, as you mentioned, it's only a tenth of the way to the moon. And when you look at it on the scale of the little videos you just showed, you can see that GEO is kind of a minuscule part of that much broader expanse of cislunar space, and it's our first step beyond that close-in neighborhood to realizing what the difficulties, the challenges, the additional needs for in-space infrastructure will be once we get to covering all of that expansive area. Now, so as a demonstration of how things grow in our perceptions over the years, we can look back to the beginning of the space age when we were putting up our first satellites, and we had this big sky theory that that space was very large and we weren't likely to fill it up, so that there was not really that much concern about hazards that we ourselves would cause. In fact, we were more concerned in the early days about collisions with micrometeoroids that might hurt our spacecraft. Now, it's much more likely in Earth orbit to be concerned about debris rather than some naturally occurring micrometeorite. So we really didn't have identification of the severity of this problem or what it could build into until about the late 70s, when some scholars studying this had come up with models that indicated that we may be on our way to a big problem here. So then it wasn't until probably in the 90s when activities by space organizations such as NASA and DoD started looking into very specific actions and putting down some rules of behavior to mitigate the problem of space debris. So then we put together, and actually NASA and DoD together developed mitigation guidelines that eventually became the U.S. government's guidelines for behavior in that respect, and put that in place by the end of 2000. And that was just the early stages of what we need to do to apply rules to our behaviors in space to sustain it for the long term. And in fact, those rules that have been in place and an additional revision to those rules that just came out in November of 2019 still don't really think beyond geo in any specific sense. I mean, there are generally applicable rules there, but there's nothing in there that says, and here's how we behave in cislunar orbits. So let me go back to George and have him talk more about what sustainability plans would look like as we move out into cislunar space.
Yes, thank you, Jim. That's a great walk down the historical development of debris mitigation practices. And as we look to the future with these emerging activities in cislunar space, we would expect that we'll need to inform our sustainability plans with at least two principal factors: the utility of a given orbit, which we can expect will correlate very strongly with the future volume of space traffic in that region, as well as the stability of the orbit, which will determine how long any debris that are generated or satellites that are kind of disposed in place will stick around in that vicinity, posing a collision risk to other operators in that environment. So just as a couple examples, I mentioned L2 earlier. The L2 halo orbits are very unique in enabling far-side lunar communications to be able to relay between the Earth's surface and anything that's habitat or rovers, for example, on the far side of the moon. That could be a real hot spot of activity. On the near side of the moon, the L1 Lagrange point, we might find spacecraft operating there, and our analyses have indicated that many transits between the Earth and the Moon actually transit that space. So it's almost like the Strait of Gibraltar in that sense, that a lot of shipping traffic may go near the L1 Lagrange point that sits about 60,000 kilometers on the earthward side of the Moon. So those are a couple places that come to mind that may warrant special attention here in terms of the orbit utility and the need for specific sustainability plans relative to those regions. In addition to protecting spacecraft operations in specific orbits, we need to give an eye to how we dispose of satellites after their mission is completed. So in addition to the typical options that we have in low Earth orbit and in GEO, for example, re-entering objects into the atmosphere either in a controlled manner or an uncontrolled manner, or putting them into long-term storage orbits that are stable and won't cause many crossings of these protected orbits in GEO, halfway between GEO and LEO, where our GPS satellites fly, as well as in LEO. We have designated areas where we can dispose of satellites today. So we've got those concepts that we could carry forward. We also can look at opportunities for active debris removal. So we might send a robotic system out to retrieve a satellite and bring it back to place for disposal or refurbishment and reuse, perhaps. Orbits beyond GEO also have a couple new options for any sample return or human crew return. Atmospheric reentry in a non-destructive sense is probably going to be heavily featured. But that's pretty expensive to bring things back to the Earth if we don't need to. So a couple other options that might be available would be to simply allow things or cause things purposefully to crash into the lunar surface. That probably has some significant regrets in terms of just the, if you will, pollution that goes on the lunar surface in so doing, and we want to be mindful of any lunar surface operations that might place in jeopardy. Perhaps the cleanest opportunity is to kick these systems out of the Earth-Moon system on a heliocentric escape trajectory. What that means is essentially you give it enough energy to depart the combined sphere of influence of the Earth and the Moon, and then go into a very long orbit about the Sun. And we have to be careful about how we do that, and examining which direction we send it and how quickly we kick it out there, so that we ensure that over quite a long time scale that it's not going to come back zipping through the Earth-Moon neighborhood and cause any problems if it does so. Considering these options, of course, debris prevention and mitigation are the first priority I would offer in cislunar sustainability. But it probably won't be perfect. It hasn't been perfect in the current paradigm in Earth orbit, so we can expect that there will be some challenges in universal adoption of these end-of-mission disposal practices, for example, in these cislunar locations. So even though prevention or mitigation is probably going to be more efficient and economical in the near term, we need to think longer term about debris remediation or cleaning up objects that get left in space. Maybe they had an anomaly and weren't able to dispose successfully. So how do we go and deal with those large objects that may be causing collision concerns for operators that share that space? The remediation techniques need to be developed, and there are some engineering challenges there. We're seeing great progress in the community on orbital servicing and active debris removal in Earth orbits. So we're starting to turn a corner on a technical standpoint. And there are some significant policies and international regulatory framework issues that need to be addressed to really fully enable the retrieval or removal of satellites that maybe another space operator left in a useful spot. So I'm going to pass it back to Jim, who's going to discuss some of those topics.
Well, I think it's obvious from what George has just described to us that the orbital debris mitigation standard practices that I mentioned earlier, initiated in 2000 and then updated in November of 2019, that's not the last word. There's more that has to be said and done to move the ball along to supervise the development and sustainability of what we do in cislunar space. And by the way, as you can see behind me, I've done a recreation of cislunar space right here at my desk. And also, here's my moon. So I got to set the standard, to set the background here, so everybody gets in the mood for this. So in the international community, once the United States developed its standard practices back in 2000, we went and we shopped them around to international forums. And to make a very long story short, we went through a couple of different international forums that created their own versions of standard practices for debris mitigation. And then at that point, it went through the UN General Assembly and got blessed by the General Assembly. Okay, well, that process from the US initiating that on the international scene to General Assembly approval was about 7 years. And that's for something that was pretty non-controversial. I mean, really, everybody was in pretty much in agreement that debris is a potential problem and we should be doing something about it. So even something where there is pretty uniform agreement, took 7 years to get through the process and make it a really worldwide accepted principle. So as we update the principles that we work on and the norms of behavior that we operate under, we have to start early because that process is going to take a long time for the next steps that we need to do for cislunar space. One of the things that, as George brought up, we are going to be moving on to an era where we're going to add, in addition to mitigation, the remediation, active debris removal. So how do we do that? Under current international law, there's a difficulty there. It is not impossible to do active debris removal, but it is a challenge because Article 8 of the Outer Space Treaty says that spacecraft remain in the ownership of the original owner in perpetuity. There is no change of ownership once there's end of life of the spacecraft, or even if it deorbits. That stays the property of the launching state forever, which means that if you want to remove some things that are cluttering up in orbit, you have to have the permission of the owner. That may sound like a simple process, but it not necessarily would be so. If the owner decides that they are not willing to cooperate, if they want to charge you a fee for doing that, if they have a very slow bureaucracy, it may be very difficult to make arrangements to clean up orbital space for things that are not under your own possession or under the jurisdiction of the United States. So what are we going to do to make the salvage in space a little bit more like salvage at sea? That's going to take some changes in the way we interpret and execute the Outer Space Treaty and other related provisions. So we have to analyze what changes need to be made, and countries very reluctant to make changes that are going to take a long time and may have implications that we hadn't realized initially. What are we going to do to make sure that we can clean up the spaceways and actually even promote a business case for doing so? So that's one thing that we have to deal with. And another is the fact that whenever you're cleaning up debris, you're dealing with proximity operations. This is scary to a lot of folks because proximity operations are the same basic technologies and techniques, whether you're doing on-orbit assembly or on-orbit repair and servicing, or whether you're doing anti-satellite weapons. So we have to come to some kind of consensus that allows that activity to go on in space without a constant fear that it's really a cover for nefarious activities. So again, this is something that is likely to take some time to work out, but it is probably going to be dependent on some of the things that George mentioned earlier that will be needed in additional in-space infrastructure, like a much greater ability to do the tracking and monitoring in the wider geographic area of cislunar space compared to the tracking and monitoring that we're doing now closer in to the Earth. So I think at that point I'll turn it back to George so he can summarize some of the things that we've talked about, and hopefully you'll take a chance to read our paper and contemplate some of the concerns that we've been pondering ourselves.
Thank you, Jim. You raised an excellent point there. In addition to the policy challenges, the coordination timelines here are very significant. So it is really a critical time as we set our eyes to expanded operations, both from the United States and other spacefaring nations beyond GEO and out into the Earth-Moon neighborhood at a much larger scale, to wrestle with these considerations and begin the coordination processes so that we can establish an international sustainability paradigm for cislunar space. To summarize, the following steps are probably going to be required in that paradigm. We'll need to extend space domain awareness sensing capabilities so that we can monitor objects and activities that go on all throughout the Earth-Moon system. There's some nascent efforts underway in the United States to examine that problem right now, and we need to continue to move in that direction so that we can operate with awareness and transparency of the various operators that are going to be venturing out to these higher altitudes. Second point I would raise in summary is that we need to formulate space traffic management protocols along with debris mitigation and disposal policies. Those are going to be really key in terms of how we share space. For example, the ITU today regulates longitude assignments and frequency allocations. There's no similar protocol for how operators might share, say, L2 halo orbit, for example. How do we keep physical distance as well as frequency deconfliction as more and more operators start to populate these points in space and these orbits with their systems? Pulling that thread of disposal opportunities a bit further, we need to continue analyses of these complex dynamics in the Earth-Moon system, and oftentimes even have to consider the long-term effects of the sun's gravity on these orbits in order to find effective methods of spacecraft disposal and to define the valuable regions that really warrant protection from disposal in place, for example. And so we need to move things out of highly used orbits and really expand the community's ability to analyze with high confidence the effectiveness of a given planned disposal trajectory to ensure that its long-term behavior is as intended, whether that's intended to crash into the moon or to depart the Earth-Moon system, to come back to the Earth, or perhaps the most difficult of these to prove over the long haul is the long-term orbit stability for a storage orbit. Finally, we need to address, as Jim mentioned, the ownership and transparency obstacles to space salvage in the current international regulatory framework so that we can enable active removal of discarded or disposed satellites if they wind up lingering in a valuable orbit that others may wish to use. So that brings us to the end of this discussion. Thank you for joining us, and we repeat our invitation to check out our paper. And it's been a pleasure talking with you about Cislunar Stewardship today.
I just have one example of some debris cleanup technology, and this is Rosie the robot, and she has with her something that is called a vacuum cleaner. See, so that is the technology, one of the technologies we will use, I am sure, as we go into the future and do some debris remediation. So I think it's back to you, Rebecca.
Thank you so much, Jim and George. I love Rosie. She's fantastic. That was great. As Jim mentioned, please go to aerospace.org/policy, download the paper, join the conversation on Twitter, hashtag the Space Policy Show, add your comments in the video box below, and join us next time. We have our 22nd episode. It's the future of commercial spaceflight with Jamie Morin and Charlie Bolden. There's going to be great discussion there. You're not going to want to miss it. Until next time, take care.